In the summer of 2004, the most famous scientist on Earth called the world's press to a conference hall in Dublin to admit he had been wrong for 30 years. Stephen Hawking had spent those decades defending an idea colleagues warned would burn down the foundations of physics, that black holes destroy information, that the universe can forget. He paid off the bet with a baseball encyclopedia. But here is what almost nobody outside that room understood. His surrender solved nothing. The question he raised in 1976 is still open tonight. The one place where quantum mechanics and gravity, our two flawless theories, flatly contradict each other about a single falling letter. Every proposed answer costs something enormous: the smoothness of space, the safety of the past, or the idea that space is fundamental at all. By the end of tonight, you will understand exactly why the person who finally solves this paradox will not just be explaining black holes, they will be explaining what reality is made of. Before we begin, if questions this large are how you like to drift off, a quick like or subscribe truly helps me keep making these. It is a small thing for you, and it means a great deal to me. Now, let's begin. Somewhere tonight, a letter is burning. Maybe it is a love letter, or a confession, or a page of secrets someone decided the world should never read. The paper curls, the ink blackens, the words dissolve into smoke and drifting ash, and the person holding the match walks away certain that what was written is gone forever. Almost everyone on Earth would agree with them, and according to the deepest law in physics, every one of them is wrong. Here is what quantum mechanics actually says about that burning letter. The words are not destroyed, they are scrambled. Every photon of firelight, every molecule of smoke, every fleck of ash carries away a tiny piece of the letter's story, encoded in its energy, its direction, its timing, its subtle correlations with every other fragment. The information has been shredded into a trillion pieces and scattered into the room, and no technology that will ever exist could practically gather it back. But in principle, and physics is a game played entirely in principle, the record survives. If you could capture every particle that left that fire, measure every property with perfect precision, and run the equations of quantum mechanics backward, the letter would reassemble. Word for word, the universe does not forget. It only files things where no one can read them. It is worth being precise about what physicists mean by that overloaded word, information, because tonight, the entire structure of reality will end up hanging on it. Information, in physics, is not meaning. It is not language or knowledge or anything a mind has to be present for. Information is distinction, the answers to every possible yes or no question about a system. Is this electron spinning this way or that way? Is this atom here or there? Is this molecule vibrating or still? Count up every distinction that makes a thing exactly the thing it is, rather than any of the countless other things it might have been, and you have counted its information. A hydrogen atom carries some. A snowflake carries more. Your body, at this moment, is a particular answer to an inconceivable number of such questions, a configuration so specific that the universe has never once repeated it, and never will. When physics says information is conserved, it is saying that the universe never collapses two different configurations into one, never rounds off, never blurs two distinct answers into a single approximation. Every distinction, once made, is permanent. The details may migrate out of the letter and into the light, but the total number of distinctions in a closed system is fixed as firmly as its energy. That is the currency we will be tracking all night, through fire and horizon and the death of stars. Not meaning, but difference. The universe, whatever else it does, is not allowed to lose track of a difference. This is not a poetic flourish. It is a mathematical property called unitarity, and it sits at the absolute foundation of quantum theory. The rule works like this. The complete quantum state of a closed system, the full description of every particle in it, evolves in time according to one equation, the Schrödinger equation, and that evolution has a remarkable character. It never merges two different starting points into the same ending point. Two different pasts can never flow into one identical future. Run the film forward or run it backward, and the mathematics works equally well in both directions, which means the present moment of the universe, fully described, contains its entire past and its entire future, not as metaphor, but as recoverable data. Physicists sometimes say it this way: quantum mechanics conserves information the way other laws conserve energy. Let that settle for a moment, because it is one of the strangest comforts in all of science. The universe keeps a perfect ledger. Every event that has ever happened, every arrangement of atoms, in every moment you have ever lived, left an entry. The entries get scrambled, encrypted, smeared across light years of radiation and dust, but the ledger itself cannot lose a page. Deleting information, truly deleting it, is the one bookkeeping crime the quantum world refuses to allow. Probabilities must always add up to 100%. If information could vanish, they would not. The whole predictive machinery of physics, the machinery that makes your phone work, that makes chemistry stable, that has been checked in some experiments to about 1 part in a trillion, rests on that ledger staying complete. And the ledger is not an abstraction confined to blackboards. It is under test, quietly, in every stable thing around you. Atoms hold their shape because quantum evolution preserves the distinctions that define them. If information could leak out of the world, matter itself would slowly lose the plot, spectral lines drifting, chemistry decaying, the crisp identity of every element blurring over cosmic time. None of that happens. The newest test is the most direct of all. Quantum computers are machines built entirely out of unitarity, devices whose every operation is a carefully choreographed information-preserving evolution, and whose worst enemy, decoherence, is nothing but information escaping into the environment faster than the engineers can fence it in. Every time one of those machines completes a computation, it is a small laboratory confirmation that quantum information behaves like a conserved fluid. It flows, it spreads, it hides, it never vanishes. The engineers fighting to keep it in, and the universe refusing to let it die, are working two sides of the same law. And notice something personal hiding inside the physics. There was an afternoon, somewhere in your childhood, that you have completely forgotten. A particular arrangement of sunlight and voices, and the exact position of every atom in your small body. You cannot recover it. No one can. But under unitarity, the universe can. In principle, that afternoon is still written into the present state of the world, dispersed into particles and fields, encrypted beyond any hope of reading. But there, forgotten is not the same as gone. Physics, as we have understood it for a century, only ever promises the first. Nothing in nature, we believed, could achieve the second. Even ordinary erasing turns out to have a price. In 1961, a physicist named Rolf Landauer showed that deleting a single bit of information from a computer memory must release a tiny, unavoidable puff of heat, a minimum toll, paid in energy, every time a record is destroyed. The point is subtle, but beautiful. Even when we think we are erasing, we are really just pushing information out into the environment, and thermodynamics charges us for the move. Information, it turns out, is not an accessory to physics. It behaves like a physical substance. It has a conservation law. It has a price list. Some physicists have begun to suspect it may be the most fundamental substance there is. There is a useful way to feel the strength of this law in your hands. Imagine filming any process in the universe. A glass shattering, a star exploding, a candle burning down, and then running the film in reverse. At the everyday level, the reversed film looks absurd. Shards leap from the floor and assemble into a glass. Smoke and ash converge and unburn into a candle. But look closely, frame by frame, at the individual particles, and nothing in the reversed film breaks a single law of microscopic physics. Every collision, run backward, is still a legal collision. Every photon absorbed is a photon that could have been emitted. The absurdity of the reversed film is not physical impossibility. It is statistical unlikelihood. The same reason a shuffled deck never happens to shuffle back into perfect order. The microscopic laws themselves have no preferred direction, and that reversibility is unitarity, wearing everyday clothes. A law that works equally well in both directions cannot destroy information, because destruction is precisely the thing that cannot be undone. For the reversed film to be even theoretically playable, and quantum mechanics insists it always is, every frame must retain enough detail to reconstruct the frame before it. The universe, in other words, is not just keeping the ledger as a courtesy. Its fundamental machinery is incapable of doing anything else. Or so physics believed, with complete confidence, for most of a century, until it met the one object whose defining feature is that nothing which happens inside it can ever be undone, outrun, or observed. So hold this picture as you settle in tonight. Reality as a ledger that cannot lose a page. A universe where burning, shredding, dissolving, and dying are all just elaborate forms of filing. This is the calm, orderly world quantum mechanics describes, and for most of the 20th century, nothing in nature seemed capable of challenging it. But the universe contains an object that appears to have been designed, almost maliciously, as a test of this exact law. An object whose entire identity is the destruction of records. An object that takes stars, planets, letters, encyclopedias, anything, and returns nothing but 3 numbers. Physics found that object not in a laboratory, but in the mathematics of gravity, decades before anyone believed it was real. And the story of what it does to the universe's perfect ledger is the story of the deepest unsolved problem in physics. A problem so central that, as we will see by the end of tonight, whoever solves it will not just be explaining black holes, they will be explaining what reality is made of. We are not ready for that claim yet. First, we need to meet the object with no memory. A black hole is what happens when gravity wins an argument it usually loses. Every star spends its life in a standoff. Gravity pulling every particle inward. Pressure from nuclear fusion pushing outward. For billions of years the standoff holds, but fusion runs on fuel, and fuel runs out. When a massive enough star exhausts itself, nothing remaining in physics can hold it up, and the core collapses, not to something small, but past every size that matters, concentrating its mass so completely that space-time itself folds around it and seals the region off from the rest of the universe. The seal is called the event horizon, and it is worth being precise about what it is, because almost everything about the paradox we are building tonight lives at this surface. The event horizon is not a wall. It is not a membrane, not a crust, not a surface you could touch. It is a boundary drawn in cause and effect, the radius at which the escape velocity, the speed you would need to leave and never come back, exceeds the speed of light. Since nothing in the universe carries information faster than light, the horizon is a one-way door in the structure of reality itself. Things go in, nothing comes out. Not matter, not light, not messages, not news of any kind. Here is the detail that should unsettle you, gently, the way it eventually unsettled the smartest people alive. According to general relativity, the horizon is locally unremarkable. If you fell through the horizon of a large black hole, the theory says you would notice nothing at that moment. No jolt, no flash, no sign. Space-time there is smooth, and the curvature at the horizon of a giant black hole is gentler than the curvature here on Earth. This blandness is not an accident. It is a direct consequence of Einstein's happiest thought, the equivalence principle, the idea that free fall erases gravity locally, that a falling observer feels no force. The most important surface in physics is by the theory's own insistence, no place at all. Remember that promise of smoothness. Before tonight is over, it will be set on fire. Now, ask the bookkeeping question. A star is an extravagantly detailed object, 10 to the 57th particles, a 1 followed by 57 zeros, each with its own position, motion, spin, and history, magnetic fields, turbulent flows, a chemical fingerprint assembled over billions of years. All of that falls inward when the star collapses. What survives, on the outside, of all that detail? 3 numbers: mass, electric charge, spin. That is the entire public record. This is one of the most remarkable results in gravitational physics, proved in stages in the late 1960s and early 1970s by Werner Israel, Brandon Carter, and others. A settled, stationary black hole is described completely by those 3 quantities. The physicist John Wheeler, the man who put the name black hole into circulation in 1967, gave the result its permanent slogan. Black holes, he said, have no hair, no features, no stubble, no birthmarks, nothing to distinguish a black hole made from a collapsed star from a black hole made from an equal mass of encyclopedias, or oceans, or love letters. Feed a black hole the complete works of every library on Earth, and feed an identical black hole the same mass in bare rock, and once the horizons settle, no measurement performed anywhere in the exterior universe could ever tell the two apart. Same mass, same charge, same spin, same black hole. The most detailed objects in the universe fall in, and the universe's most perfect amnesiac swallows the file. Notice what this does to the perfect ledger we opened with. When the letter burned, the information escaped into the room, scrambled, but out there, recoverable in principle. When the letter crosses an event horizon, nothing escapes into the room. The room is sealed by the geometry of space-time itself. The details are not shredded and scattered. They are removed from the reachable universe and replaced, on the outside, by 3 entries on an index card. For a while, physics had a soothing answer to this, and it is worth taking seriously, because it held the line for decades. The answer was, hidden is not erased. The information is not gone. It is inside. Behind the horizon, all those particles and their histories still exist, still evolve, still carry their records. We simply cannot look at them. The ledger has a locked drawer, and a locked drawer is annoying but legal. Unitarity does not require information to be accessible. It only requires it to exist. If black holes lived forever, the drawer would stay locked forever, the file would sit safely inside, and quantum mechanics could keep its accounts with a shrug. An eternal black hole is not a paradox. It is only a secret. And through the middle of the 20th century, that is exactly what black holes were believed to be. Eternal. Final. The mathematics of general relativity contained no mechanism, none, by which a black hole could shrink, leak, or give anything back. They were the universe's dead ends, cold and permanent. The places where stories went to stop being told. Frozen stars, the Russians called them. Objects with no temperature, no glow, no future. Just mass, charge, spin, and silence, until the end of time. The idea's own history is a story of disbelief slowly losing ground. As early as 1783, the English clergyman John Michell reasoned that a star 500 times the size of ours would pull hard enough that even light could not leave it. A dark star, invisible by construction. Laplace toyed with the same thought in France, and quietly dropped it from later editions of his book. Einstein's own equations produced the modern version within weeks of their publication. Karl Schwarzschild, calculating in a wartime field hospital in 1915, found the exact geometry with its fatal radius. And Einstein spent years insisting nature would never actually build such a thing. In 1939, Robert Oppenheimer and Hartland Snyder showed that nature has no choice. A sufficiently massive star, once its fuel is spent, collapses past every barrier, and the horizon forms according to the plain arithmetic of gravity. Even then, most of physics looked away for another generation, until the objects began, one by one, to show up. An X-ray source in the constellation Cygnus, discovered in 1964, behaved exactly like a star being devoured by an invisible companion too heavy to be anything else. In 2015, the gravitational wave detectors heard two black holes, 36 and 29 times the mass of our Sun, spiral together and merge, the waveform matching Einstein's mathematics to the decimal. And in 2019, a planet-wide network of radio telescopes produced the first image of a horizon's shadow, a ring of orange light around a darkness 6.5 billion times the mass of our Sun, followed, 3 years later, by the portrait of the 4 million solar mass giant at the center of our own galaxy. The point of this parade, for tonight, is single and sharp. The object with no memory is not a thought experiment. The universe manufactures them by the hundreds of millions. Whatever the paradox decides about reality, it will be deciding it about real places, some of them in our own neighborhood. The soothing answer had one hidden assumption, that the drawer stays locked, that black holes really are forever, that nothing ever comes back out. In 1974, a 32-year-old physicist in Cambridge, working the entire calculation in his head because his hands could no longer hold a pen, discovered that the assumption is false. Black holes leak. The drawer is not locked, it is evaporating, and the way it evaporates is precisely what turns a locked drawer into the deepest crisis in modern physics, because the leak, when he examined it, was carrying nothing. The most careful calculation anyone had ever performed at the edge of a black hole said the universe's ledger does not just have a locked drawer, it has a shredder, and the man who found it had been trying to prove the opposite. The crisis began, as many of the best crises in physics do, with a graduate student asking an innocent question about a cup of tea. The student's name was Jacob Bekenstein, and in the early 1970s, he was working at Princeton under John Wheeler, the same Wheeler who named black holes and declared them bald. Wheeler posed a puzzle to his student, half as a joke. Imagine, he said, that I take a hot cup of tea, an object full of disorder, thermal jostling, molecular chaos, what physicists call entropy, and I drop it into a black hole. The tea is gone. Its disorder is gone with it. And the second law of thermodynamics, the rule that says the total entropy of the universe can never decrease, seems to have been quietly robbed. The universe's disorder went down, and the evidence fell behind a horizon where no auditor can follow. Have I just committed the perfect crime? The second law is not a minor rule. It is the law that gives time its direction, the reason cream stirs into coffee and never stirs back out, the reason the past looks different from the future. Arthur Eddington once wrote that if your theory is found to be against the second law of thermodynamics, there is nothing for it but to collapse in deepest humiliation. And here was a chalkboard argument suggesting that any black hole is a machine for breaking it, a cosmic paper shredder for entropy itself. Bekenstein took the joke seriously, and in 1972 he proposed something that sounded absurd to almost everyone who heard it. The entropy is not destroyed, he argued. It is transferred. The black hole itself must have entropy, and its entropy is written on its surface. Bekenstein had noticed a suspicious coincidence. A theorem proved shortly before by a young Cambridge physicist named Stephen Hawking showed that in any natural process, the total surface area of a black hole's event horizon can never decrease. Area only grows. Drop the teacup in, and the horizon swells, just slightly, a quantity that can only increase, attached to every black hole in the universe. Bekenstein looked at Hawking's area theorem and said, That is not like entropy. That is entropy. When the T falls in, its disorder is not deleted from the accounts. It is credited to the black hole, recorded as area, and the second law survives, now covering black holes too. There was a problem with this beautiful idea, and the problem's name was Stephen Hawking. Hawking thought Bekenstein was misusing his theorem, and he had a devastating objection. In physics, entropy and temperature travel together. You cannot have one without the other. If a black hole has entropy, it must have a temperature, and anything with a temperature must radiate, must glow, at least faintly, the way a warm ember glows in infrared. But a black hole is, by definition, the one object in the universe that cannot emit anything. Its temperature must be exactly zero. Therefore, its entropy was meaningless. In 1973, Hawking and two colleagues, James Bardeen and Brandon Carter, published a paper laying out the laws of black hole mechanics, which looked uncannily like the laws of thermodynamics, and they included a pointed remark that the resemblance was only an analogy. The glow was impossible. The student was wrong. To finish the argument, Hawking decided to do the one calculation nobody had seriously attempted, to bring quantum mechanics itself to the edge of the horizon. Not a full quantum theory of gravity, nobody had one, and nobody has one now, but a careful hybrid. Quantum fields, the fizzing, fluctuating fabric of matter and light, calculated on top of the curved space-time of a collapsing star. He wanted to check, with full quantum rigor, exactly what an observer far from a black hole would detect. He expected the answer to be nothing. He was building the tombstone for Bekenstein's idea. Picture the scene, because it deserves to be witnessed. It is the winter of 1973, going into 1974, in Cambridge. A 31-year-old man sits in a wheelchair, in a small office, thick with chalk dust and cold English light. Motor neuron disease has already taken his ability to write. A calculation that would fill 100 pages must be held entirely in his mind, the way a chess master holds a game. Vacuum modes tracked one by one through the warping space-time of a collapsing star, each term carried, checked, and set aside, for weeks. Colleagues remember him sitting very still for hours, then dictating a correction. And somewhere in those weeks, the calculation begins to disobey him. He is hunting for zero, for the clean silence that will put Bekenstein's entropy in the ground. Instead, a flux keeps appearing. Something is coming out. He assumes he has made an error. He runs the mind chess again. The flux survives. He tightens the approximations. It survives. The black hole in his equations is not silent. It is glowing, faintly, steadily, with the exact spectrum of an ordinary warm object. He will later admit he was annoyed. The radiation was ruining his argument. It took him weeks more to believe his own result, and when he finally presented it, he did so almost apologetically, under a title with a question mark in it, as if hoping someone would talk him out of it. Black hole explosions? No one talked him out of it. The paper appeared in Nature in March of 1974, and its full version, Particle Creation by Black Holes, followed the next year. The result is now called Hawking radiation, and it rearranged the furniture of physics. Black holes are not black. They shine, in the coldest, dimmest way imaginable, but they shine. They have a genuine temperature, inversely proportional to their mass. Small holes run hot, giant holes run almost unimaginably cold. And with a real temperature, Bekenstein's entropy became real too. Hawking, the man who had set out to destroy the idea, ended up proving it and fixing its exact value. The entropy of a black hole equals 1/4 of its horizon area, measured in the smallest units of area the universe allows. His own tombstone would one day carry the formula. The formula deserves a moment of quiet appreciation, because the quantity it defines is not modest. Entropy counts hidden arrangements, the number of microscopic ways a system can be assembled while looking the same from outside. And for black holes, The count is computed in the smallest tiles the universe permits, units of Planck area, squares roughly 10 to the minus 70th of a square meter, so small that a single proton's cross-section contains about 10 to the 40th of them. Cover the event horizon in these tiles, take a quarter of the count, and you have the black hole's entropy. For a black hole the mass of our Sun, the number that comes out is around 10 to the 77th power, a 1, followed by 77 zeros. For comparison, the actual Sun, with all its churning plasma and tangled magnetic fields, carries an entropy of about 10 to the 58th. Collapse the same material into a black hole, and its entropy multiplies by a factor of 10 to the 19th, 10 billion times more hidden arrangements in the same mass. Black holes are not merely entropic, they are the most entropic objects the laws of physics allow, the densest possible filing of hidden information in any region of space. Tally the whole observable universe, and the conclusion is almost comical. The entropy of all the stars, gas, light, and neutrinos combined is a rounding error next to the entropy of the supermassive black holes. Almost all of the universe's hidden information, by an overwhelming margin, is filed behind horizons. Whatever black holes are doing with information, they are not doing it at the margins of the cosmic economy. They are the cosmic economy. Bekenstein, for his part, paid for the idea before being paid for it. He was a young man with almost no standing, born in Mexico City to Polish immigrants, trained in the United States, later a professor in Israel, publicly contradicting the leading gravitational physicists of the age, and the initial reception ran from skepticism to something closer to scorn. Hawking himself would recall finding the proposal offensive in its apparent misuse of his theorem. Bekenstein absorbed the criticism, refined the argument, and formulated what is now called the generalized second law, the total entropy of the universe, ordinary entropy outside horizons, plus 1/4 of the total horizon area, never decreases. It is the second law of thermodynamics, amended to survive a universe containing black holes, and half a century of scrutiny has failed to break it. Wheeler, who had posed the teacup joke in the first place, reportedly told his students something worth keeping. An idea crazy enough to be interesting deserves to be published, because if it is wrong, little is lost, and if it is right, everything changes. It was right. Everything changed. Stop and appreciate what had just happened, because it is one of the great reversals in the history of science. Thermodynamics, the humble physics of steam engines and teacups, had reached across a century and planted its flag on the strangest object in general relativity. The three great pillars of physics, quantum mechanics, gravity, and heat, had met for the first time in a single formula, and the formula worked. Bekenstein's teacup was safe. The second law held everywhere. It looked, for a moment, like a triumph of unification. The universe's ledger seemed stronger than ever. But you already know enough, from everything we have built tonight, to feel the trap being assembled beneath the celebration. A glow is not just a glow carries energy, and energy leaving a black hole means the black hole is losing mass. The eternal object, the locked drawer, the final resting place of all those detailed histories. It was never eternal at all. It is a fire, the slowest fire in the universe, burning its own mass as fuel, and burning toward a very specific, very dangerous ending. To understand where the radiation comes from, you have to change your picture of empty space. What we call vacuum is not nothing. Quantum field theory, the most precisely tested framework in all of science, describes empty space as a restless medium, seething at the smallest scales with fluctuations, fields trembling around zero, pairs of particles and antiparticles flickering into a brief borrowed existence and cancelling away again, everywhere, always, including in the darkness between your ceiling and your closed eyes right now. In ordinary space, the books always balance. The fluctuations borrow energy and repay it so fast that nothing permanent is ever created. The vacuum hums, but it hums evenly. An event horizon ruins the bookkeeping. Near the horizon, the smooth vacuum humming is pulled apart by the geometry itself. The cleanest way to say it, and every popular picture here is a loose translation of harder mathematics, is that the horizon splits the vacuum's correlations. One partner of a fluctuation falls inside, carrying negative energy as the accounts are settled. The other escapes outward as real radiation. The black hole pays the energy bill for making that escaped particle real, and it pays out of the only account it has, its own mass. Particle by particle, the black hole spends itself into the sky. The pace of this spending is almost beyond patience. A black hole with the mass of our Sun would have a temperature of about 60 billionths of 1 degree above absolute zero. 60 billionths. The cosmic microwave background, the faint afterglow of the Big Bang that fills all of space, is about 2.7 degrees above absolute zero, which makes the universe itself roughly 45 million times warmer than the black hole, and heat flows from warm to cold. So today, every stellar black hole in the sky is a net absorber, drinking in more energy from starlight and the cosmic background than it releases. The fire is lit, but for now, the rain falls harder than the fire burns. It is worth lingering on how gentle these numbers are, because they are among the most restful facts in physics. 60 billionths of a degree is a temperature beyond the reach of natural intuition. The coldest laboratory apparatus humans have ever constructed, the great dilution refrigerators that host quantum computers, hover thousands of times warmer. If you stood, impossibly, safely, a fixed distance from a solar mass black hole with a perfect detector, you would wait, on average, ages between individual quanta of its glow, arriving with any meaningful energy. The brightest thing about a black hole is everything around it, never the hole itself. And the coldness is not incidental to the story. It is the story. An object this cold emits radiation, whose typical wavelength is comparable to the size of its own horizon. Light waves kilometers long, carrying almost nothing, one after another, for spans of time that reduce every other patience in nature to a rounding error. Whatever mechanism eventually smuggles a star's worth of information out through this whisper has to work through the dimmest, slowest, most miserly channel the universe possesses. Keep that dimness in mind through everything that follows. The entire crisis of modern physics travels, if it travels at all, on the faintest light there is. Evaporation only wins in the far future, when cosmic expansion has stretched the background radiation colder than the holes themselves. Then, with nothing left to feed on, each black hole begins its long spending in earnest. And long is not a word that does the timescale justice. The evaporation time grows with the cube of the mass. For a black hole the mass of our Sun, about 10 to the 67th power years, a 1, followed by 67 zeros. The universe so far has lasted about 14 billion years, a 1, followed by roughly 10 zeros. If the whole history of the cosmos to date were a single second, the evaporation of one stellar black hole would take longer than a billion ages of the universe. The giants at the centers of galaxies would take up to 10 to the 100th power years, numbers so large that calling them astronomical is an insult to them. There is one loophole in the patience, and it comes with its own persistent myth, worth retiring here. Because the temperature runs inversely with mass, a small enough black hole is not cold at all. It is ferociously hot, and it burns out fast. A black hole the mass of a mountain would be finishing its evaporation about now if the early universe happened to mint such primordial black holes in its first violent fraction of a second. Astronomers have searched for the telltale final flashes for decades, so far without a confirmed detection, and the search is one of the few conceivable ways Hawking's radiation could ever be observed directly. The myth is the mirror image of this fact. The recurring worry that a particle collider might make a small black hole and doom the Earth. The same physics that raises the worry retires it. Any microscopic black hole the Large Hadron Collider could conceivably produce, and standard gravity says it cannot reach remotely far enough down to try, would be so small and so hot that it would evaporate in about 10 to the minus 27th seconds, gone before crossing a single atom's width. And nature has been running the experiment for free throughout history. Cosmic rays, carrying far more energy than any accelerator, have hammered the Earth, the Moon, and every star in the sky for billions of years, and everything is still here. The fire we are describing tonight is real, but it points its danger inward, at the black hole itself, and at a conservation law. Let yourself drift into that future for a moment. This is a place worth visiting slowly. You are standing, bodiless, patient, outside of time's ordinary concerns, in the space where a galaxy used to be. The stars burned out long ago, the last red dwarfs guttered and went dark when the universe was 1,000 times its current age, and that was, from where you now float, almost infinitely long ago. The sky is not black the way a night sky is black. It is black the way closed eyes in a dark room are black. Perfect. Total. The cosmic background radiation, once a warm glow filling the sky, has been stretched by expansion into a whisper too cold to measure. And ahead of you, invisible, sits the last inhabitant of this region, a black hole that was born from a star when the universe was young, and has spent every era since then, slowly, silently turning its mass into light too dim for any eye. For a length of time no story can hold. Nothing here changes. Then, near the very end, the pace quickens. Smaller means hotter. Hotter means faster. Faster means smaller. In its final week, the black hole is brighter than a star. In its final second, it releases a flood of high-energy radiation, the closest thing to a shout it has ever made. A flash. In the deepest dark there will ever be, and then nothing. The region is empty. Where a star's worth of matter once folded space-time around itself, there is only outgoing radiation, spreading into the endless cold. Now ask the departing light the only question that matters tonight. Somewhere in that radiation, in its frequencies, its timing, its correlations, is there a record? The star that collapsed all those ages ago had a composition, a history, a spin, a magnetic personality. 10 to the 57th particles, each doing something particular. The universe keeps a perfect ledger. We began the night with that promise. So, where in this last light are the entries? Hawking's calculation had an answer, and the answer is the reason this video exists. The radiation is thermal, perfectly, blandly thermal, the same featureless spectrum an oven produces, described completely by a single number, the temperature. A thermal spectrum is nature's blank page. It is what radiation looks like when it carries no message at all. The glow depends only on the black hole's mass, charge, and spin, the same 3 numbers on the index card, and on nothing else. Nothing about the star, nothing about the encyclopedias, nothing about the letter. 2 black holes with identical index cards, one built from a star and one built from every library on Earth, would evaporate, according to the mathematics, into radiation that is identical in every measurable way, down to the last particle. The drawer did not open at the end. The drawer dissolved, and what came out was static. We should be careful and honest here, because this is the hinge of the whole night. This conclusion comes from Hawking's original, approximate calculation, quantum fields, on a fixed, classical spacetime. Whether that approximation can be trusted about the information is exactly the war we are about to enter. But taken at face value, the result is as clean as it is catastrophic. The black hole forms, the details go in, the black hole evaporates, only blankness comes out, and at the end, there is no black hole left to hide anything inside. The locked drawer was the universe's alibi. Evaporation takes the alibi away. Stephen Hawking saw the implication immediately, and in 1976, he published the claim that would define the next 50 years of fundamental physics. We have been circling it all night. Now we are ready to look at it directly. The paper Hawking published in 1976 carries one of the most quietly alarming titles in the scientific literature: Breakdown of Predictability in Gravitational Collapse. Not breakdown of a model or of an approximation. Breakdown of predictability, the load-bearing wall of physics itself. His argument has the simplicity of a trap that has already closed. Follow the state of the universe through the life of one black hole. Before the collapse, there is a star, and a star, however complicated, is in principle a pure quantum state. A single, definite, exquisitely detailed wave function. The kind of state the perfect ledger is made of. The star collapses. A horizon forms. The details take shelter behind it. Then, over 10 to the 67th power years, the black hole converts itself entirely into Hawking radiation. And Hawking's calculation says that radiation is thermal, featureless, random in the deepest sense. Here is why that word thermal is fatal, and it is worth slowing down for, because the entire 50-year war turns on it. In quantum mechanics, there is a sharp mathematical distinction between two kinds of state. A pure state is a complete description, the universe's actual entry in the ledger, containing every detail and every correlation. A mixed state is an admission of ignorance, a probability distribution over possibilities, the kind of description you use for a coin under a cup, when the answer exists but you do not know it. Ordinary physics moves pure states to pure states, always. That is unitarity. That is the never-merging, always reversible evolution we met at the start of the night. Burning a letter takes one enormous pure state to another enormous pure state, and the appearance of randomness in the smoke is only ignorance. The details are there, just unreadable. Thermal radiation is not like the smoke. A truly thermal state is mixed all the way down. Its randomness is not a disguise over hidden detail. There is no hidden detail. Ask what is beneath the probabilities, and the answer is nothing. So if a star, a pure state, collapses and evaporates into exactly thermal radiation, a mixed state, then somewhere in that process, the universe's actual entry in the ledger was not scrambled, not encrypted, not hidden. It was converted into blankness. Two different stars, a ball of hydrogen and a ball of encyclopedias, every possible different past, would end as the same featureless static. Distinct pasts, flowing into one identical future. That is precisely the thing unitary evolution can never do. The film of the universe would no longer run backward. The present would no longer contain the past. To feel the difference in your hands, set the two fires side by side. The letter in the fireplace. To any human observer, its randomness and a black hole's randomness look identical. Smoke is as unreadable as static. But the smoke's randomness is a locked diary, and the radiation's randomness, in Hawking's mathematics, is a blank diary. The locked diary frustrates you. The blank diary has nothing in it to frustrate you with. Every practical test you could run tonight would fail on both. The distinction lives entirely at the level of principle, in whether a perfect intelligence, Laplace's old demon upgraded with quantum instruments, could in principle reverse the process. For the fireplace, yes, always yes. For the black hole, Hawking said, no, not hard, not encrypted, no. The reconstruction fails because there is nothing left to reconstruct from. And physics is a game played entirely in principle. Its laws are not summaries of what is convenient to measure. They are claims about what the universe can and cannot do at all. One single counterexample in principle, one letter, one star, one bit, and the law is not weakened. It is false. Hawking did not flinch from this. He asserted it. Gravity, he argued, is the one force that breaks quantum mechanics' deepest rule. Put a horizon in the story, and information really is destroyed, not hidden, destroyed. God not only plays dice, he wrote, but sometimes throws them where they cannot be seen. It remains one of the most elegant sentences ever attached to a scientific claim, and notice exactly what it says. Einstein's old complaint was that quantum mechanics is a casino. Hawking's claim was worse. The casino sometimes throws the dice into a pit, and the roll, the actual outcome, the fact of the matter, is not merely unseen, but expunged from the universe. Hawking did leave himself, over the years, one softer variation on the theme, and it is worth a paragraph because it shows how strange the acceptable exits already looked. Perhaps, he and others speculated, the information is not destroyed but exiled, carried by the collapsing matter into a disconnected pocket of space-time, a baby universe pinched off at the singularity, forever causally separated from ours. In that picture, the ledger of the whole multiverse balances. It is only our branch office that shows a loss. The proposal was never developed into a working theory, and its accounting is cold comfort. For every observer who could ever exist in our universe, exiled information is exactly as gone as destroyed information. The film of our world still cannot be run backward using anything our world contains. But notice what the existence of the proposal concedes. To save the ledger from the black hole, one of the most conservative minds in gravitational physics was willing to invoice the bill to unobservable universes. The paradox was already showing its defining talent, making every escape route cost more than the crime. So now the trap is fully visible, and we can state the black hole information paradox in its complete form. 3 statements, each near the heart of physics. 1. Quantum mechanics is exactly right. Evolution is unitary, information is never destroyed, the ledger is perfect. 2. General relativity is right about horizons. The event horizon is locally smooth and unremarkable, and whatever falls through it cannot influence the outside. 3. Hawking's semi-classical calculation is trustworthy where it seems safe to trust it. Quantum fields on gently curved spacetime, far from the singularity, producing thermal radiation. Each statement is backed by mountains of evidence, and they cannot all be true. If the radiation is thermal to the end, unitarity dies. If unitarity survives, then the information somehow gets out. But nothing can get out through a horizon without breaking relativity's causal structure, or the smoothness Einstein promised. Something at the foundation, quantum law, the shape of space-time, or our right to combine them, is wrong. It would take the community years to feel the full force of this. In 1976, black holes were barely accepted as real astronomical objects. A bookkeeping crisis scheduled for 10 to the 67th power years in the future struck many physicists as a curiosity, a puzzle for the philosophers. The paradox spent its first decade as a side conversation, but paradoxes at the foundation do not stay side conversations, because a contradiction between your 2 best theories is not a fact about black holes. It is a fact about the theories, available for inspection now, tonight, anywhere in the universe. The black hole is merely the courtroom where the case finally comes to trial. It is fair to wonder why physicists lose sleep over a bookkeeping dispute scheduled for 10 to the 67th power years from now. And the answer says something lovely about how physics works. The theories in conflict are not files of predictions. They are engines of inference, and we use both engines, together, every single day. The same quantum field theory that predicts the thermal radiation underwrites every transistor in the device playing this video. The same general relativity that draws the one-way horizon corrects the clocks of the satellites that told your phone where you are today, to within a few meters. When 2 engines that reliable produce contradictory outputs from the same input, the contradiction is not a curiosity about the far future. It is a bug report filed against the present. Somewhere in the machinery we are using tonight, an assumption is quietly false, and has been false all along, in every calculation, in every laboratory, in every device, harmlessly so far, but false. Paradoxes of this kind are the most valuable objects in science, precisely because they are bug reports from reality itself. The last time physics held one this fundamental, the ultraviolet catastrophe, a century and a quarter ago, resolving it required inventing quantum mechanics. Physicists lose sleep over the information paradox because they know what its resolution is likely to cost, and what the last resolution of this size bought. And before we watch the war begin, we should ask the question a reasonable, sleepy mind might ask at this point. Would it really be so terrible? Suppose Hawking was simply right. Suppose the universe does destroy a little information, in the most exotic corners, over the longest conceivable times. The ledger loses the occasional page in a fire. Who exactly gets hurt? The answer, it turns out, is everything, everywhere, immediately. And understanding why is the next step down. Physics has a way of punishing small crimes with large sentences. The reason is that its laws are not a list of independent rules. They are a woven structure, each thread holding tension for the others. Pull one, and distant parts of the fabric move. In 1984, three physicists, Tom Banks, Michael Peskin, and Leonard Susskind, decided to find out what actually happens to the fabric if you pull the unitarity thread. They tried to build, carefully and sympathetically, a version of quantum mechanics in which information can be destroyed the way Hawking proposed, a modified evolution law where pure states can honestly become mixed. What they found became one of the most cited warnings in theoretical physics. The information loss did not stay in the black hole. In their analysis, the same mechanism that lets a black hole erase a bit tends to infect the quantum vacuum everywhere, because in quantum field theory, the exotic and the everyday share the same underlying fields. The vacuum, remember, seethes with virtual processes. Anything the laws permit at a horizon, the vacuum will sample in miniature, everywhere, all the time. Allow information destruction, and generically you allow tiny random kicks in the bookkeeping of energy itself. Their conclusion: theories that destroy information tend to violate the conservation of energy, not dramatically, at first, but everywhere at once, in a way that would heat empty space. Your bedroom would run a fever, courtesy of black holes 10,000 light-years away and ages hence. The effect would have shown up in laboratories long ago. It has not. Another exit was priced during those same years and found similarly expensive: the remnant. Suppose evaporation simply stops, that when a black hole shrinks to the smallest scale physics permits, around the Planck mass, roughly 0.02 of a milligram, quantum gravity halts the burning and leaves a stable ember. The information never escapes and is never destroyed. It sits, forever, inside the ember. The bookkeeping balances, and the price is absurdity by a different door. A remnant would be an object smaller than any measurable size, lighter than a grain of dust, obligated to store, without limit, the complete file of whatever black hole it came from, up to 10 to the 77th bits in a speck, with no ceiling, since the parent hole could have been any size. Objects with unbounded internal states and bounded mass-rec quantum field theories accounting, they should be produced in unlimited swarms by ordinary processes, from the energy of empty space itself, and plainly are not. Like the baby universes, remnants survive in the literature as a minority position rather than a refuted one. Physics is careful with words like impossible. But the pattern of the ledger's defenses was becoming visible. Every exit from the paradox was turning out to cost a foundation. It remained only to discover which foundation the universe had actually chosen to spend. There are loopholes and rebuttals. Physicists such as William Unruh and Robert Wold have argued for decades, carefully and honorably, that information loss can be tamed, that the heating argument is not airtight, and their position deserves respect. It is the minority report, not a fringe. But the Banks-Peskin-Susskind result reframed the paradox for good. Losing information is not a small crime with a distant victim. The perfect ledger is not one law among many. It is load-bearing. Energy conservation leans on it. The stability of empty space leans on it. Every probability in physics, summing to 100%, leans on it. Let one black hole burn one true page, and the fire spreads backward into the foundations of everything. There is a quieter way to feel the stakes, without any equations at all, and it may stay with you longer than the technical argument. Think again about the difference between forgotten and gone. Everything you have ever lost is, tonight, merely forgotten. The voice of someone you loved who is no longer here. The exact sound of it, the precise waveform that left their body and crossed a room and entered your ears on some ordinary afternoon. That pattern spread outward, thinned, was absorbed into walls and air and other lives, scrambled into the world's noise. You will never retrieve it, but under the laws of physics as we have believed them for a century, it was never destroyed. The pattern still exists, dispersed through the state of the universe, encrypted by complexity, the way the burned letter still exists in the light and ash. Physics has never promised us access. It has promised us existence, that the past, all of it, remains a fact, written somewhere in the present, however unreadable. The universe remembers even when we cannot. There is a strange comfort in that, and you have been living on it, probably without knowing, your entire life. Information loss revokes the promise. If Hawking was right, then the universe contains machinery, real machinery, sitting tonight at the center of our own galaxy, 4 million times the mass of our sun, that does not scramble the past but abolishes it. Facts that were facts would stop being facts. Not hidden, not forgotten, withdrawn from reality, the way a number is erased from a blackboard, leaving not even the claim that it was ever written. The past itself would become perishable, safe only as long as it stays away from horizons, and in the far future, nothing stays away from horizons forever, and the machinery is not remote. Tonight, as you listen, the black hole at the center of our galaxy, the one whose portrait humanity captured in 2022, is holding, behind its horizon, the complete files of everything it has consumed across billions of years. Stars that formed before the Earth existed, clouds of gas that might have become worlds, every particle documented, under quantum law, down to the last distinction. Under Unitarity, all of it remains part of the universe's record, held in trust, scheduled for release over 10 to the 90th years of patient light. Under information loss, that region of the sky is something else entirely, a growing hole in the record itself, an archive fire burning in slow motion, 4 million suns of forgetting. Both descriptions refer to the same coordinates, the same darkness, the same photograph. Choosing between them is not a matter of taste, and physics could not leave the choice unmade forever, because the difference between a library and a shredder is not a philosophical nuance. It is the difference between a universe in which the past is a permanent fact and one in which the past is a temporary arrangement. Every argument in the remaining hours of tonight's story is, at bottom, about which universe you are lying in right now. That is what it would cost to lose. And that is why, when the implications finally sank in, some physicists refused, flatly, professionally, for decades, to accept it. One of them, a particle physicist from the Bronx, with a gift for slogans and a street fighter's patience, decided that Hawking's claim was not a discovery, but a declaration of war. He would spend 20 years assembling the counterattack. The dispute he started would come to be called the Black Hole War, and it is the story of how the paradox went from a curiosity to the center of theoretical physics, and of how, along the way, physicists began to suspect that the answer would demand a price no one expected, not a repair to quantum mechanics, and not a repair to relativity, but a rebuild of the idea of space itself. Leonard Susskind heard Stephen Hawking present the information loss claim in a small workshop in San Francisco in 1981, in the attic of a mansion owned by a physics-loving businessman. Decades later, he would describe the moment in almost physical terms, the feeling that something had been said which could not be allowed to stand. Gerard Hooft, the Dutch theorist who would later win a Nobel Prize for taming the mathematics of the weak force, was in the room and reacted the same way. Most of the audience nodded along with Hawking. Those two could not. Both men had spent their lives inside quantum field theory, where unitarity is not a preference but the engine block, and both walked away convinced that the smiling man in the wheelchair had made a subtle, profound error, and that finding it would require taking black holes more seriously than even Hawking had. It is worth pausing on the shape of this disagreement, because it was unusually pure. Nobody disputed the calculation. Hawking's mathematics was checked and rechecked, and it held. The dispute was about jurisdiction, about which law bends when two absolute laws collide. Hawking, the relativist, held that space-time geometry is the deeper truth. If the horizon's causal structure says information cannot escape, then quantum mechanics must yield. Susskind and Hooft, the field theorists, held the mirror position. Unitarity is the deeper truth, and if the horizon seems to forbid it, then our picture of the horizon is wrong. Same equations, opposite loyalties. For roughly a decade, the war stayed cold. Position papers, conference skirmishes, no decisive weapon on either side. The two dissenters were, in style, almost comic opposites. Susskind, raised in the South Bronx, a plumber's son who worked his father's trade before physics found him, brought a brawler's instinct for the argument that ends arguments, and a conviction he stated without apology: the ledger is not negotiable, and anyone who thinks otherwise has not understood what quantum mechanics is. He would later write an entire popular book about the dispute and title it, without irony, The Black Hole War. That Hooft, precise, formal, already among the most decorated theorists in Europe, arrived at the same conviction from pure structure. He had spent his career proving that quantum field theories keep their accounts to fantastic precision, and he was not prepared to believe nature ran a rigged branch office at every horizon. It matters that both men were particle physicists rather than relativists. They had spent their working lives in the one corner of science where unitarity is tested daily, where every collision at every accelerator balances its books to the last decimal. To them, Hawking's proposal was not radical open-mindedness. It was an accounting error made by someone who had never been audited. The counterattack, when it finally took shape in the early 1990s, was built from an idea with a deceptively modest name: black hole complementarity. Susskind, working with Laurus Thorlacius and John Uglum, proposed that the paradox dissolves if you give up something nobody had thought to question: the assumption that there is one single, observer-independent account of where things are. Consider the letter falling toward the horizon and follow it twice. Seen by the letter itself, in free fall, nothing happens at the crossing. It sails through the smooth horizon Einstein promised, into the interior, carrying its words with it. Seen from outside, by a distant observer, relativity's time dilation takes over. The letter's final approach stretches over longer and longer external time, and the letter appears to slow, flatten, and halt just above the horizon, never quite crossing. Susskind and his collaborators took that second picture seriously as physics, not appearance. In their proposal, everything that falls toward a black hole is, from the outside universe's point of view, caught and scrambled in a hot, quantum-active layer just above the horizon, a stretched horizon, where it is churned into the subtle correlations of the outgoing Hawking radiation and eventually returned to the universe. From the outside, the information never went in, and unitarity is safe. From the inside, the letter crossed smoothly, and Einstein is safe. Two stories, flatly contradictory, about one letter. The outside story was not conjured from convenience. It grew from mathematics the relativists themselves had built. Astrophysicists modeling real black holes had long since discovered that, for every practical purpose, a black hole behaves exactly as if its horizon were a physical membrane, a surface with measurable electrical resistance, viscosity, and temperature, which conducts, dissipates, and heats like matter. The membrane paradigm, they called it, and it was understood as a brilliant bookkeeping fiction. Susskind's move was to ask the question the fiction had been politely avoiding: what if the membrane's properties are not a fiction? Quantum mechanics adds its own ingredient. Time dilation at the horizon does not merely slow the falling letter's image. It spreads the letter's quantum information across the stretched horizon's degrees of freedom, scrambling it at what would later be proved the fastest rate any physical system can achieve. Black holes, in this picture, are not the universe's vaults. They are its fastest shredders, with the crucial difference, on which everything hangs, that a shredder preserves every scrap. Complementarity's defense was as audacious as the contradiction. No observer can ever collect both stories. The outside observer can never look behind the horizon. The infalling observer can never report back. The contradiction exists only on the blackboard of an imagined referee standing outside the universe, and physics, Susskind argued, owes consistency only to observers who actually exist. It was quantum complementarity, wave and particle, position and momentum, promoted to space-time itself. Where a thing is, whether it has been destroyed or preserved, became observer relative at the deepest level. If that made philosophers dizzy, Susskind considered the dizziness a fair price for saving the ledger. And beneath complementarity sat an even stranger discovery, one we have met before on this channel, from a different road. Remember Bekenstein's entropy, proportional to the horizon's area. Entropy counts states. States store information. So the maximum information a black hole can hold scales not with its volume, as it would for any ordinary object, books, hard drives, brains, but with the area of its boundary. Work out what that implies, and you arrive at the holographic principle proposed by Hooft and sharpened by Susskind in the mid-1990s. The complete physics of any region of space can be encoded on that region's boundary surface, the way a two-dimensional hologram encodes a three-dimensional image. If you have spent other nights with this channel, you have seen where that principle eventually led. For tonight, keep only the clue that matters for our paradox. Information in gravity does not live where naive intuition puts it. It lives on surfaces. The horizon, the surface, was never an absurd place for the star's file to end up. It may be the most natural filing cabinet in the universe. A caution belongs here, because this idea has escaped into popular culture in a distorted form. When physicists say the world may be holographic, a certain corner of the internet hears the universe is a simulation, a rendering, a video game, information because someone is computing it. That is not what the physics says, and the distinction matters. The holographic principle is a statement about capacity and bookkeeping, that the number of distinctions a region of space can hold scales with the area of its boundary rather than its volume, a fact forced on physics by black hole thermodynamics, with no programmer anywhere in the argument. It is a discovery about how much reality fits in a box, not a claim that the box is plugged in somewhere. Nothing in the mathematics implies a simulation, points to one, or needs one. The principle would be exactly as true and exactly as strange in a universe that is the only thing that has ever existed. The honest version is stranger than the fiction anyway. The fiction merely relocates reality to someone else's computer. The physics suggests something with no relocation available. That surface and interior, boundary and bulk, may be two complete descriptions of one thing, and that neither is more real than the other. In 1997, the idea received its most powerful supporting evidence from a young Argentine theorist named Juan Maldacena, who found an exact mathematical equivalence between a certain universe with gravity and a quantum theory without gravity living on that universe's boundary, a working hologram in full mathematical detail. We gave that discovery its own night on this channel, and one paragraph is all it needs here. But the paragraph is decisive. In Maldacena's mirror world, black hole formation and evaporation is described exactly and completely by an ordinary quantum system on the boundary, and ordinary quantum systems are unitary, period. Within that framework, information cannot be lost, any more than a game of chess can end with pieces having vanished from the recorded moves. For many physicists, this settled the verdict of the war. But notice the fine print, because the next 20 years of our story live inside it. The boundary description proves the information survives, without showing how it escapes the horizon. It is a conviction without a confession. The dictionary between the hologram and the interior remained, and in large part remains, untranslated at exactly the entry marked where. That same year, the war acquired its famous piece of paper. Stephen Hawking and Kip Thorne on one side, John Preskill on the other, drew up a formal wager at Caltech. Hawking and Thorne bet that information swallowed by a black hole is destroyed, hidden forever from the outside universe, as general relativity's horizon seemed to demand. Preskill bet that quantum mechanics would win. The information must escape, encoded somehow in the evaporation. The stake, in the great tradition of physics bets, was an encyclopedia of the winner's choice, from which the wager document notes with a straight face, information can be recovered at will. The document itself, posted for years on Preskill's university webpage, reads like a legal contract drafted by people enjoying themselves, whereas Stephen Hawking and Kip Thorne firmly believe that information swallowed by a black hole is forever hidden, and whereas John Preskill firmly believes that a mechanism for the information to be released must and will be found, therefore the parties resolve, and so on, with signatures. Beneath the comedy sat a perfectly serious sorting of the field. Two relativists, raised inside Einstein's geometry, wagering that geometry wins. One quantum information theorist, wagering that the ledger wins. The bet was made in February of 1997, and it is a detail worth savouring that within that same year, Maldacena's discovery would land, and the ground under the geometric side would begin, almost imperceptibly at first, to move. Let us take the midpoint of our night, here at the war's height, to lay the pieces on the table one more time, slowly. The universe keeps a perfect ledger. Quantum evolution never destroys information. That is the first piece, and everything from your phone to the stability of atoms testifies for it. Black holes have no hair. Whatever falls in leaves only mass, charge, and spin on the outside. That is the second piece, proved from Einstein's own equations. Black holes glow and die. Hawking's radiation, born from the vacuum at the horizon, blank and thermal in his calculation, spends the whole away to nothing over 10 to the 67th power years. That is the third piece. And the three pieces cannot fit in the same universe. Either the ledger burns with the black hole, and with it the foundations of quantum mechanics and perhaps energy conservation itself, or the blank radiation is secretly a courier, carrying the file out in correlations we have not learned to read, at the price of rewriting what horizons, locations, and space itself mean. That is the whole war, restacked. Hold it gently. Everything that remains tonight is the story of how physics chose the second option, and what the choosing has cost so far. Because the war, at this point, still lacked something essential, a referee. Complementarity was a philosophy. Holography was a principle. The Maldacena result was a verdict from a mirror world whose translation was incomplete. What nobody had was a precise, quantitative test. a number that unitarity demands, that Hawking's calculation refuses, calculable on both sides and compared. Without one, the two camps could argue jurisdiction forever. The test existed, as it turned out. It had been published years earlier, in 1993, by a soft-spoken professor in Edmonton, Alberta, who had once been Hawking's own doctoral student, and who had asked the one question precise enough to hold the entire paradox on a single curve. Don Page is not a famous name outside physics, and inside physics he is famous partly for being unclassifiable, a devout Christian, a meticulous calculator, a man who did his doctorate under Hawking at Caltech and Cambridge in the 1970s, lived in Hawking's house as a graduate assistant, helped him begin each working day, and then spent a career, with evident affection, politely explaining why his mentor was wrong about information. Where others argued philosophy, Page asked an accountant's question. Fine, he said, in effect. Suppose quantum mechanics is exactly right, and a black hole's evaporation is unitary from start to finish. What, precisely, would we see? Not in slogans, in numbers. What does the radiation have to do, and when does it have to do it? The tool for the question is entanglement entropy, a number that measures how much a piece of a quantum system is bound up with the rest, how much of its apparent randomness is really shared correlation. And in 1993, Page computed how that number must behave for the radiation leaving any evaporating system that obeys quantum law. The result is a curve, and the curve has become so central to fundamental physics that it is simply called the Page curve. It looks like a tent. In the early life of the black hole, each Hawking particle that escapes is entangled with the interior it left behind. The radiation, examined alone, looks random, and its entanglement entropy rises, particle by particle, exactly as Hawking would predict. Nothing forbidden yet. Early randomness is fine, the way the first half of any encrypted file looks like noise. But entanglement is a strict currency. A black hole of a given size has only so much capacity. Bekenstein's area entropy counts it, and as the hole shrinks, its capacity shrinks with it. There comes a moment, roughly halfway through the evaporation, when the shrinking hole can no longer hold up its end of the entanglement. Page showed that if unitarity is true, the curve must turn over at that moment, the famous Page time, and descend, all the way back to zero by the final flash. Past the peak, the radiation must stop looking like fresh randomness and start paying out pattern. Each new particle must arrive correlated with the particles that came before, knitting the earlier noise into meaning, the way the last chapters of a mystery novel convert every stray detail into structure. By the end, the radiation as a whole must be a pure state, the star's file, complete, translated into light. Hawking's calculation draws a different line. In the strictly thermal picture, every particle is fresh randomness forever. The entropy rises and never comes down, and when the black hole vanishes, the curve is left hanging at its maximum, a mountain of unresolved entanglement with a partner that no longer exists. That dangling curve is information loss, drawn as a picture. Feel what Page had accomplished, because it changed the character of everything. The deepest dispute in physics, decades of philosophy about observers and jurisdictions, and the meaning of space-time, had been compressed into a single, brutally concrete question. Which line does nature draw? Up forever, or over the tent? One curve or the other? No rhetoric, no interpretation. And notice the quiet violence of the halfway clause. The turnover does not happen at the end, in the final exotic flash where anything might be forgiven. Unitarity sends its bill at the midpoint, when the black hole is still enormous, still calm, still exactly the kind of object Hawking's approximations should describe flawlessly. Whatever mechanism rescues the information cannot hide in the last instant. It has to be operating in broad daylight, at a huge, ordinary horizon, 10 to the 66th years before the story ends, while every equation we trust insists the horizon is smooth, quiet, and locally empty. For a decade and a half, the page curve sat in the literature like a verdict waiting for a case. Neither side could compute the actual curve for a real black hole. Gravity's entanglement bookkeeping was beyond anyone's mathematics, but the target was now drawn, and everyone knew it. Reproduce the page curve from gravity itself, and unitarity wins. Fail forever, and Hawking wins. Page's curve also carried a corollary so strange it took the field years to absorb, worked out in 2007 by Patrick Hayden and, fittingly, John Preskill. They asked a mischievous question: past the page time, once the radiation holds more than half the entanglement, how long would a freshly dropped secret stay hidden inside the black hole? The answer astonished even specialists. For an old black hole, information tossed in is returned to the radiation almost immediately, scrambled at the fastest rate nature allows, then re-emitted, recoverable in principle by anyone patient enough to have collected the earlier light. An old black hole, they showed, behaves not like a vault but like a mirror, with a delay measured in scrambling time. For a solar mass hole, about a millisecond. Page himself, through all of this, remained the argument's quietest participant, a man whose contribution was not a faction but a standard. He had run the numbers in the early 90s on a desktop computer, in papers so unassuming that their titles give no hint. A 50-year war was being decided in them, and then he simply waited, revising and extending the calculation as the decades passed, answering objections with more calculation. There is a species of scientific courage in that patience, worth naming for anyone lying awake tonight with an unsolved problem of their own. Page did not know which side of the war was right, and unlike nearly everyone else in the story, he declined to pretend otherwise. What he knew was the shape any right answer would have to have, and he was content to let the shape do the arguing. 26 years passed between the curve's publication and its derivation from gravity. In science, being correct early is common, and being useful early is common. Being exactly, quantitatively correct about the form of an answer nobody could compute for a quarter of a century is close to unique. When the derivations finally arrived, the highest compliment the field could pay was already fixed in the vocabulary. Nobody had to explain what it meant, that gravity had produced the page curve. The result sharpened the paradox's absurdity to a razor edge. The same object that general relativity describes as the most perfect prison in nature is described by quantum mechanics, in its old age, as approximately the most efficient publisher in nature. Both descriptions were now quantitative. They could not both be the whole truth, and the gap between them was no longer philosophical. It was a factor that could be written on one line. Hawking, for his part, spent those years defending the rising line, and then, in the summer of 2004, he stopped. Dublin, Ireland, the 21st of July, 2004. The 17th International Conference on General Relativity and Gravitation, GR17, in the trade, is the kind of meeting that normally unfolds in comfortable obscurity. A few hundred specialists, parallel sessions on gravitational lensing and numerical methods, coffee in styrofoam cups. Not this year. This year there are television crews in the aisles and reporters from around the world holding paper cups they have not touched, because word went out in advance. Stephen Hawking has requested a special session. After 30 years, he is ready to concede on the deepest problem he ever posed. Picture the auditorium as the lights settle. It is standing room only. In the front, the wheelchair, and the stillness particular to Hawking's lectures. Every sentence assembled in advance, delivered by the synthesized voice that had become, by then, one of the most recognizable sounds in science. He begins, with the dry timing he loved, by noting the unusual interest. He wonders aloud whether the press has come, hoping he will announce that black holes are portals to another universe. He will disappoint them. What he announces instead, sentence by patient sentence, is an accounting. He has redone the problem with new methods. He now believes the evaporation is unitary after all. Information, he tells the room, is not destroyed. The featureless radiation is not featureless in the final reckoning. The correlations are there, and everything that falls in comes back out, transformed beyond recognition, but never expunged. There is no baby universe carrying the lost file elsewhere, he says. The information was never lost at all. He is, in the careful language of a man surrendering a fortress he built himself, reversing the claim of 1976. His stated reasons, published in fuller form the following year, turn on a technical shift with a poetic shape. His new calculation summed over geometries, over different possible spacetimes at once, including, alongside the black hole, configurations with no horizon at all. And in that larger sum, the no-horizon possibilities carry the information out, however small their weight. A horizon, in this picture, is never a certainty. The universe always keeps a channel open. Few specialists found the specific argument decisive on its own. It was schematic where the difficulty is sharpest. But as an act of scientific character, the moment stands almost alone. The most famous scientist alive had spent 30 years as the public face of a position. And when the balance of evidence moved, he moved, at 72, in front of the world's cameras, with a joke and an encyclopedia. Whatever else the paradox has cost physics, it produced one of the clearest public demonstrations on record that in science, held long enough and honestly enough, even the deepest conviction is refundable. And then the moment the cameras came for. The terms of the 97 bet called for an encyclopedia from which information can be retrieved at will. Hawking has chosen, with a comedian's precision, Total Baseball, the ultimate baseball encyclopedia, over 2,600 pages of the most lovingly recorded statistics any civilization has kept, flown from the United States because no bookshop in Ireland stocked it. John Preskill comes forward to accept. And Preskill, a reserved, rigorous man, chair of Caltech's particle theory group, does something colleagues will tease him about for years. He hoists the enormous book over his head with both hands, grinning like a shortstop who has just won the World Series, while the flashbulbs go off. It is one of the strangest images in the history of physics. The world's most famous scientist conceding the nature of reality, and the prize is batting averages. Hold the frame a second longer, because the room itself deserves remembering. Sitting in those seats are people who have spent, collectively, centuries on this one question. Students who became professors while it stayed open, rivals who built careers on opposite answers, young researchers who have never known a physics without the paradox in it. When the concession lands, the applause is long, and by several accounts, there is something in it beyond politeness. The sound of a field, acknowledging that an era has been closed by the man who opened it. Somewhere in the applause, too, there is unease, and the sharpest people in the room can name it. A concession is not a mechanism. They are applauding a verdict nobody can yet derive. Preskill will say later that what he truly wanted was not the book, but the understanding, and that the understanding, on that day in Dublin, was still nowhere in the building. But stay in the room a moment longer, past the flashbulbs, because 3 details in that auditorium tell you the war did not actually end that day. Detail 1. Kip Thorne does not concede. Hawking's own teammate on the bet, sitting in that same hall, tells the press he wants to see the argument in detail before he gives up on information loss. The bet's losing side splits in public, on stage. Detail 2. Preskill himself, holding his trophy, tells reporters, candidly, and to his lasting credit, that he does not fully follow the calculation he has supposedly won by. Hawking's new argument, sketched in the lecture and published the next year, uses a technical approach that most experts found suggestive rather than decisive. The The community's quiet consensus was that Hawking had been persuaded by the total weight of the field, above all by Maldasena's hologram, where unitarity is manifest, and had then constructed his own route to a conclusion others had reached before him. The referee had changed his call, but no one could quite reconstruct the replay. Detail 3, and this is the one to carry to the end of the night. Nothing in the concession said how. Grant that the information escapes. By what mechanism? Through what channel does the file cross a smooth horizon that relativity says is a one-way door? At what moment? Carried by which particles? Evading which theorem? Silence. The most famous surrender in modern physics settled the verdict and left the crime unexplained. The page curve still had no derivation from gravity. The horizon was still smooth in every equation anyone trusted. The paradox had not been solved. It had been voted on. There is a human ledger to close here too, and it deserves a quiet paragraph. Stephen Hawking spent 30 years, nearly half his life, defending information loss, alone at the end, against most of his field, and when he finally moved, it was on an argument built with tools that were never his own. He did not stop working the problem. In 2016, at 74, he returned to it with Malcolm Perry and Andrew Strominger, chasing a new idea called soft hair, the proposal that the vacuum itself can be subtly imprinted at a horizon, that Wheeler's bald black hole secretly keeps records after all, written in zero-energy whispers of light and gravity at its edge. It was his final sustained scientific effort. He was still pursuing it when he died, in March of 2018, at 76. And here is the fact that gives this chapter of the story its particular ache. The breakthrough, the one we have been building toward all night, the calculation that finally drew the page curve out of gravity's own mathematics and showed, in principle, that his radiation carries the file, arrived in 2019. 1 year after his death, the man who lit the fire, who fed it for 40 years, who conceded his own position and then kept digging anyway, missed the answer's first light by a single year, after waiting 45. He is buried in Westminster Abbey, between Newton and Darwin. Carved on the stone is his temperature formula, the equation of the radiation that started it all. The stone, of course, states the formula without comment. It does not say where the information goes. In 2018, no one on Earth could have written that line. The soft hair idea he left behind deserves one more sentence of respect, because it planted a flag exactly where the field was about to dig. The no-hair theorems assumed the vacuum around a black hole is unique, one and only one state of empty space, so that settling into it wipes every record. Hawking, Perry, and Strominger argued the assumption fails. Empty space at a horizon comes in infinitely many, gently distinct versions, differing by soft quanta, particles of light and gravity with vanishingly small energy, undetectable as energy, but real as record. A black hole that swallows a letter does not settle into the vacuum, it settles into a vacuum, one delicately different from the vacuum next door, and the difference is a memory. Whether soft hair could store all of the file, or only its outermost layer, remained, and remains, unsettled. But the reframing was prophetic. The records were never going to be found in what the black hole is. They would be found in what the black hole leaves, in the exact, patient fine print of its emptiness and its light. And before anyone could, the paradox had one more escalation to deliver, because in 2012, 4 physicists in Santa Barbara examined the polite truce that complementarity had brought, and found that it does not merely bend the rules of quantum mechanics. It breaks them. If information really escapes, they argued, then something is waiting at the horizon of an old black hole, something Einstein's smooth, uneventful, promise-keeping horizon could never allow, a wall of fire. The argument arrived in the summer of 2012 from Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, 4 theorists at Santa Barbara, whose initials, AMPS, became its permanent name. On its surface, the paper was a technical audit of black hole complementarity. In substance, it was a demonstration that the peace treaty everyone had signed after Dublin was unsigned all along, that unitarity, Einstein's smooth horizon, and ordinary physics outside the horizon form a triangle in which some side must break, not may break, must. The weapon is a principle we have not yet needed tonight, and it is one of the least negotiable in all of quantum theory: the monogamy of entanglement. Entanglement, the profound quantum correlation between systems, is not a mood. It is a strictly budgeted resource, and the budget's sternest clause says that maximal entanglement is exclusive. If particle A is maximally entangled with particle B, then A cannot be entangled with C at all. Not weakly, not a little. The mathematics of quantum states simply has no room for it. As absolute as 1 + 1 refusing to equal 3. Any story that requires one particle to be strongly entangled with two different partners at once is not describing our universe. Monogamy can be made intuitive, with a homely picture. Entanglement is often described as two particles sharing one secret. Measure either one, and you learn the shared answer. The sharpest form of the principle says a perfect secret can only be shared two ways. If a third party knows it, it was never a perfect secret between the first two. Whatever correlation the third party holds must have been carved out of the original bond, weakening it. This is not a rule about etiquette, but about the geometry of quantum states. The mathematics that defines maximal entanglement simply contains no configuration in which it points two directions at once. Cryptographers stake real money on this daily. Quantum key distribution works precisely because any eavesdropper who becomes correlated with the key necessarily damages the correlation between the honest parties, and the damage is detectable. So when the firewall argument found a particle contractually obligated to share a perfect secret with two different partners, the early radiation by unitarity, its infalling twin by smoothness, the conclusion was not that black holes are unusually complicated. It was that at least one of the contracts is void. Now watch the trap assemble itself, because AMPS built it from three commitments the field had already made, each one defended earlier tonight. Commitment 1, the page curve. If evaporation is unitary, then past the halfway point, each newly emitted Hawking particle must arrive strongly entangled with the earlier radiation. That is precisely how the tent-shaped curve descends, how the noise gets knitted into meaning. So consider one particle, call it B, emitted from an old black hole, past its page time. Unitarity demands B is strongly entangled with the early radiation, the enormous cloud of quanta emitted over the ages before it. Commitment 2, the smooth horizon. Hawking radiation is born at the horizon as one half of a vacuum fluctuation. B escapes outward, while its partner, call it A, falls inward. And here is the point where Einstein's promise becomes a precise quantum statement. A smooth, uneventful vacuum at the horizon, the no-drama crossing that the equivalence principle guarantees, mathematically requires that B and A be maximally entangled with each other. That entanglement is not decoration, it is what smoothness is, in quantum terms. Delicate correlations between the two sides of any surface are exactly what it means for that surface to be empty space rather than a wall. Break the entanglement between outgoing and infalling partners, and the energy stored in those severed correlations becomes real, violent, and local. The vacuum at the horizon tears into a curtain of high-energy quanta. Commitment 3. Nothing unusual operates outside the horizon, where curvature is gentle, and our tested physics should apply without correction. Count the entanglements assigned to particle B, maximally entangled with its infalling partner A, Einstein's requirement. Strongly entangled with the early radiation, Page's requirement, if the ledger balances. One particle, two exclusive marriages. Monogamy says, impossible. The triangle has no interior. something breaks. Amps then walked, with unsettling calm, through the exits. Give up the page curve entanglement, and you have given up unitarity, information loss again, with all the poison we priced in Part 6. Give up ordinary physics outside the horizon, and you have declared that quantum field theory fails in regions indistinguishable from the space in your bedroom. Or give up the third thing, give up smoothness. Cut the bond between B and A at the horizon of every old black hole, and accept what the cutting physically means. The severed vacuum does not stay empty. The horizon of an old black hole becomes a firewall, a surface of ferocious quanta at which anything arriving, dust, letters, astronauts, is not gently admitted to an interior, but incinerated at the edge, its story ending in fire, at a place general relativity swears is nowhere at all. In the firewall picture, an old black hole may have no interior in any meaningful sense. The inside of the universe's most famous objects would be, quite literally, nothing. To feel what is at stake, make the crossing yourself. You are falling toward a black hole of 1 billion solar masses, enormous, ancient, its horizon wider than our solar system, its tides at the crossing gentler than the gravity in your bedroom. This is Einstein's version of the moment. You watch for the horizon and cannot find it. There is nothing to find. No marker, no membrane, no change in the light. The crossing arrives and passes, and you feel nothing, precisely nothing, the most carefully predicted nothing in science, the equivalence principle, keeping the promise it has kept since Einstein first imagined a falling man in 1907. You are inside. The universe you left glows behind you, and ahead, still far away, the interior waits. Now run the same approach in the amps version. Same black hole, same trajectory, same gentle tides, and at the same unmarked radius, where the other story offered silence, this story offers a curtain of quanta at energies beyond any accelerator, the shredded remains of a century of severed vacuum correlations, waiting at the exact surface Einstein promised was no place. You do not cross the horizon in this version. You end at it. Two impeccable theories, one crossing, and physics, for the first time in its history, genuinely unable to tell you which experience is true, the silence or the fire. The firewall paper detonated across theoretical physics. Joe Polchinski himself, by every account one of the most careful and least sensational thinkers of his generation, described the conclusion as one he did not want and could not evade. He had, colleagues said, disproved his own side's truce and reported it anyway, because the mathematics left him nowhere else to stand. Rebuttals arrived within weeks, then dozens more, then hundreds. New entanglement structures, modified interiors, radical proposals connecting the interior to the radiation by geometry itself. One famous response argued that entangled particles might be secretly linked by microscopic wormholes, an idea we have explored on another night and will touch only lightly here. Since the word wormhole has now entered the room, one honest sentence should close the door that popular culture leaves open. None of this, not the firewall debate, not the geometric rescues proposed against it, makes black holes portals, in the traveller's sense. The interior of a real black hole leads to a singularity, not to an elsewhere. The wormholes in these arguments are untraversable by construction, incapable of carrying a signal, let alone a ship, and keeping any wormhole open for passage would require negative energy in quantities no known process in the universe supplies. When physicists speak of connections between the interior and the radiation, they mean connections in the entanglement accounting, bridges in the mathematics of correlation, not tunnels in the sky. The real result is stranger than the fantasy, in the way this subject keeps making familiar. The fantasy just relocates you through space, while the physics quietly questions what space is. No rebuttal achieved consensus. What the firewall achieved instead was clarity of a merciless kind. After amps, there was no comfortable position left anywhere on the board. Every camp, information loss, complementarity, firewalls, exotic interiors, now had to pay openly in some currency the field had once considered sacred: quantum law, or the smooth space-time of Einstein, or the reality of the black hole interior itself. Even Hawking, watching from Cambridge in his final years, was moved to one last public provocation. In early 2014, he posted a short, sketch-like note suggesting that the firewall crisis should be resolved by demoting the event horizon itself, replacing the absolute once-and-forever boundary with an apparent horizon, a provisional surface that can trap light for eons and then, in a full quantum treatment, eventually release everything. Headlines around the world announced that Stephen Hawking had declared black holes do not exist, which was not what the note said, but the misreading contained a seed of the truth. The most famous name in the field was conceding, in his own way, what amps had forced everyone to confront: that some cherished piece of the classical black hole, the eternal horizon, the untouchable interior, the perfect one-way door, was going to have to be given up on purpose, by somebody, soon. The only argument left was over which piece, and the argument had stopped being polite. Joe Polchinski, for his part, carried the firewall with visible discomfort until his death in 2018, the same year as Hawking, telling interviewers he hoped someone would prove his own argument wrong. Few sentences capture that strange decade of physics better. The authors of the sharpest result in the field, publicly rooting against themselves, while the equations refused to cooperate with anyone's hopes. 8 years after Dublin, the war Hawking had conceded was fully reopened, and the question stood sharper than it had ever stood in 40 years. If the file gets out, and holography insists it does, then something must carry the interior's information into the radiation without setting the horizon on fire and without breaking the rules of entanglement. Nothing anyone had written down could do it. What no one knew, as the firewall arguments burned through the 2010s, was that the answer's first draft was only a few years away, and that it would come not from a new principle or a new object, but from gravity's own oldest tool, asked one question no one had thought to ask it. The mathematics of Einstein was about to draw the page curve with its own hand, and the price of the drawing would be the strangest yet: pieces of the black hole's interior, reassigned, by entanglement itself, to the radiation in the sky. The breakthrough came in 2019, and like many true breakthroughs, it came twice at once. Jeffrey Pennington, then a graduate student at Stanford, and independently a team of 4, Ahmed Almheri, Netta Engelhardt, Donald Marolf, and Henry Maxfield, attacked the problem with a strategy that sounds almost too modest to work. They did not propose a new theory of quantum gravity. They did not invent new particles, new dimensions, or new principles. They took the ordinary, semi-classical tools, gravity as Einstein wrote it, quantum fields as Hawking used them, the very apparatus that had produced the paradox, and they recomputed one quantity with more care than anyone had ever applied to it: the entanglement entropy of the Hawking radiation as a function of time. They asked gravity itself to draw the curve. Rises forever, and Hawking's information loss stands. Turns over at the page time, and the ledger survives. The tool that made the difference is called the quantum extremal surface prescription, a rule refined over a decade of work on holography for computing entanglement entropies in gravitating systems. The rule contains an instruction that sounds innocent. To find the entropy of a region, you must search over all possible surfaces that could bound the relevant degrees of freedom, compute a certain quantity for each, part geometric area, part quantum entropy, and then take the surface that gives the smallest answer. Gravity, in other words, is contractually obligated to use the best available accounting. The prescription did not appear from nowhere. It is the summit of a 15-year staircase, and one step deserves naming even in passing. In 2006, Shinsuke Ryu and Tadashi Takayanagi discovered that in holographic universes, the entanglement entropy of a boundary region is computed by a startlingly geometric rule. Find the minimal surface hanging into the interior and measure its area, entanglement, computed with a tape measure by the same quarter area law Bekenstein and Hawking found for horizons. It was the first hard evidence that entanglement and geometry are not merely related, but interchangeable, that the amount of quantum correlation between two regions is the area of the surface that separates them. A decade of refinement taught the rule to include quantum corrections and to locate itself without a boundary's help, and by 2019 it had matured into the quantum extremal surface prescription, the instrument finally sensitive enough to weigh a black hole's radiation honestly. The point of the genealogy is its moral. The tool that resolved the page curve was built, piece by piece, from the discovery that space-time geometry is entanglement bookkeeping. The paradox was solved, to the extent it has been, by taking that identification seriously and following it all the way down. And in 2019, the calculations revealed that partway through a black hole's evaporation, a new accounting becomes available. One that nobody had ever included, because it seems to break the most basic rule of geography. Here is what the mathematics found. Early in the evaporation, the standard accounting wins. The radiation's entropy is just the sum of its escaped quanta, rising exactly as Hawking said. But the rising account grows more and more expensive, and at almost precisely the page time, a second configuration undercuts it. A configuration in which the entropy of the radiation outside the black hole is computed by including a region inside the black hole. A large region, most of the interior in fact, everything deeper than a thin zone near the horizon. The calculation gives this region a name that has already entered the permanent vocabulary of physics: the island. Past the page time, gravity's own bookkeeping declares that the island, the interior of the black hole, the place the infalling partners went, the locked room itself, no longer counts as the black hole's private property. For the purposes of entanglement, for the purposes of information, the inside of the black hole belongs to the radiation outside it. Sit with that sentence, because it is the strangest official statement mathematics has ever made about space. The interior does not move. Nothing crosses the horizon outward. No signal, no particle, no cause violates the one-way door. And yet, in the entanglement ledger, which, if the holographic lesson is right, is the more fundamental ledger, ownership of the interior quietly transfers to the light in the sky. The infalling partners, the ones whose severed bonds threaten to build the firewall, are not severed after all. They sit on the island, and the island is part of the radiation. So the partners are, in the accounting that matters, already outside. The monogamy crisis dissolves. Particle B's two marriages turn out to be one marriage, described twice. And when the entropy is tallied along this new accounting, the curve stops rising. It turns over. It descends along page's tent, all the way to zero at the final flash. Semi-classical gravity, the same mathematics that created the paradox in 1976, computes, when asked with sufficient care, the unitary answer. Hawking's tools, in the hands of a generation that includes people born after his concession, drew the page curve. The hair was there all along. Wheeler's slogan, "Black holes have no hair," turns out to have been not a verdict about nature, but a confession about where physics had been looking. The hair was never going to be found on the black hole. It was written into the radiation, into correlations spanning ages of emission, and into the fine print of an entanglement contract that assigns the very interior of the hole to the light that left it. Hawking's soft hair program, his final effort, is now seen by many as an early sighting of the same fine print. The horizon's records, kept in whispers nobody had thought to audit. And how does the calculation know? What is the machinery, inside the mathematics, that reaches across the horizon and files the interior under radiation? This is where the story becomes both wonderful and honestly unfinished. and honest is what we will be. The turnover is enforced within the calculation by contributions called replica wormholes. To compute entanglement entropy, physicists use a standard trick. Imagine several copies, replicas, of the entire evaporating system, side by side, and compute a quantity that compares them. When Pennington and Almheri, Engelhardt, Marolf and Maxfield, and their collaborators performed this computation through gravity's path integral, the sum over every possible geometry, Feynman's method applied to spacetime itself, they found that gravity insists on including geometries in which the replicas are connected. Wormholes, threading from the black hole interior in one copy to the black hole interior in the next. These connected geometries are exactly what unseats the forever rising curve and enthrones the island. Take them out by hand, and you recover Hawking's answer and lose the ledger. Leave them in, and the path integral demands they stay in, and unitarity emerges from Einstein's own equations. The papers landed in the field like rain after a 40-year drought. Within months, the calculations had been reproduced, translated into half a dozen formalisms, and extended from the simplified models of the first derivations toward ever more realistic settings. Within 2 years, Ireland had gone from a coinage in 2 manuscripts to a standard chapter heading in graduate courses. A generation of physicists raised on the slogan "It from qubit," trained equally in gravity and in quantum information, fluent in error-correcting codes and entanglement measures in a way no previous cohort of relativists had been, treated the result less as a shock than as a homecoming. The tools they had spent a decade sharpening on holograms turned out to be the tools the 50-year problem had been waiting for. There is a lesson about science folded quietly into that timing. The page curve was derived not when the problem became important, it had been important for half a century, but when a community finally existed that could hold both of the colliding theories as native languages. Paradoxes, it seems, are not solved by the generation that discovers them. They are solved by the generation they create. Be very clear about what these wormholes are and are not, because the border between the two is the current edge of human knowledge. They are not tunnels in the sky. Nothing travels through them. They connect mathematical replicas of the universe inside a calculation, not 2 places you could visit. Some physicists believe they are pure accounting devices, the shadow, cast on approximate tools, of some deeper exact theory we have not written. Others suspect they are telling us something true and radical about reality, that spacetimes which seem separate are sewn together beneath the level of geometry, and that this sewing is what entanglement is. That suspicion has a famous earlier form, the conjecture that every pair of entangled particles is connected by a microscopic, untraversable bridge of geometry, an idea we gave its own hearing on another night, and which stands tonight as one more signpost pointing in the same direction as the islands. The signs all point one way, and none of them yet says how far. It is worth pausing over what the island result does to the older pictures we met tonight, because in the calm of hindsight, it is gentler than a revolution. It is an arbitration. Complementarity claimed the interior and the radiation were 2 descriptions of one file, and was accused of philosophical convenience. The islands make the claim a theorem of the entropy accounting, with the boundary of the island drawn at a computable radius. The firewall said the interior of an old hole could not exist alongside unitarity. The islands answer that it exists, but is not independent. The interior is unburned precisely because it is not a second copy of the information, but the same copy, counted from inside. Even Hawking's original calculation is honored in the settlement. Every individual quantum of radiation is exactly as thermal as he computed. What he could not include, because the tools did not exist, was the global fine print, the replica wormhole correlations that bind ages of thermal static into a single pure state. Everyone, in a sense, was holding one true edge of the same object. The object itself, the thing of which geometry and entanglement are two faces, still has no name and no equation of its own. Finding it is the open assignment. Honesty also requires saying plainly where the island results stop. The cleanest derivations were performed in simplified arenas, lower dimensional model universes, and settings with special boundary conditions where the mathematics can be held entirely in view, and their extension to the astrophysical black holes above our heads is argued, with good reasons, rather than proved. The calculations deliver the entropy curve, which is an audit, not a narrative. They certify that the books balance without exhibiting any particle-by-particle story of how a given bit crosses from interior to radiation, and physicists who ask for that story, a mechanism you could follow in time, at the horizon, in our universe, are still asking an open question. Some in the field suspect the demand for such a story is itself the last classical prejudice, the audit being all there is at the fundamental level. Others suspect the mechanism exists and will name the true microscopic carriers of gravity's information when it is found. On this, the honest report from the frontier is the oldest sentence in science. We do not know yet. Said, in this field, with the particular contentment of people who finally, after 50 years, know exactly what it is they do not know. So this is where the 50-year war stands as you drift tonight. The verdict is in, as firmly as theory can deliver one without experiment. The information escapes. The page curve turns. The universe's ledger balances, even across the death of a black hole. The final flash of that last evaporating hole, in the far future we visited hours ago, carries, encrypted in correlations spread across 10 to the 67th years of faint light, the full file of the star that died to make it. But the verdict has been delivered without a mechanism. The island rule works. Nobody can yet say what it is a rule about. The wormholes appear in the mathematics. Nobody can say what they connect in reality. The interior belongs to the radiation. Nobody can say what that sentence means in the language of things moving through space. Because, increasingly, the suspicion is that it cannot be said in that language at all. And that suspicion is the door to the final part of tonight's story. The reason this one paradox, born from a teacup and a question mark, has come to be seen as the master key. It is time to cash the promise in our title. Every great paradox in the history of physics has been a message in disguise, and the message is always the same sentence with a different subject. Your concepts are too small. The ultraviolet catastrophe, the 19th century's absurd prediction that a warm oven should blaze with infinite energy, was not a fact about ovens. It was the quantum world announcing itself. The paradox of light's constant speed, the same beam measured identically by observers rushing toward it and away, was not a fact about light. It was space-time announcing itself, and Einstein was the one who listened. A true paradox is never a problem in the world. It is a seam in our description of the world, the visible stitch where two ideas that cannot both be fundamental have been sewn together and worn as if they were one garment. The black hole information paradox is the largest seam ever found, because the garment it runs through is everything. On one side, quantum mechanics, the perfect ledger, tested to a part in a trillion, the operating system of matter. On the other, general relativity, the smooth geometry of space and time, tested from falling apples to colliding black holes a billion light-years away. Each is, on its own ground, the most successful theory our species has produced. The paradox is the one place where their claims about a single object, one letter, falling through one horizon, returned as light, cannot be reconciled by politeness. And so it is the one place where the successor to both theories is forced to show itself. That is not rhetoric. We have watched it happen all night. Every serious answer to the question, where does the information go, has been forced to legislate about reality itself. Information loss legislates that the past is perishable, and the quantum ledger approximate. Remnants legislate infinities into dust-mote objects. Complementarity legislates that where things are is observer relative. Firewalls legislate that Einstein's happiest thought fails at the door of every old black hole, and that the interior of the universe's most common giant objects may not exist. And the islands, the current best answer physics owns, legislate strangest of all, that the connectivity of space, the plain question of which regions are part of which systems, is not fundamental at all, but is written and rewritten by entanglement. That interior and exterior, here and there, inside and outside, are entries in the quantum ledger rather than facts of geography. The radiation in the sky can own the inside of a black hole. Distance, adjacency, the membership of space in systems, negotiable. The ledger, never. That is the emerging lesson, stated as plainly as the current frontier allows. In the contest between space-time and information, space-time blinked. The geometry Einstein taught us to see, as reality's stage looks, from inside this paradox, like an approximation, a smooth, human-scale summary of something deeper, the way temperature is a smooth summary of molecular storms. And the deeper thing, whatever its final mathematics turns out to be, appears to be made of quantum information, patterns of entanglement, stitched so densely and so consistently that they wear the appearance of continuous space, of patient time, of a universe with insides and outsides. Space as the hologram, entanglement as the film. If that is right, and islands, holography, and every signpost of the past 30 years lean that way, then the question hiding inside our title was never really about black holes. To explain how one file crosses one horizon, you must state what space is made of, when its geometry can be trusted, and what the universe is doing at the level beneath both quantum mechanics and gravity. There is one seam, and it runs through everything. Whoever solves this paradox will solve reality itself. The title of tonight's story is not an exaggeration. It is, as far as physics can currently see, a job description. The most precise description we have of what the next Einstein will actually have to do. What makes the assignment unlike any previous one in physics is that the experiment may never come to help. Every previous revolution had laboratories forcing its hand, spectra that would not fit, orbits that would not close. Here, the decisive data sits behind the faintest signal in nature. The Hawking glow of any real black hole is tens of millions of times colder than the microwave background it would have to be read against. And the paradox-resolving correlations are subtler still, spread across epochs. Physicists have built laboratory analogues, sonic horizons in ultra-cold fluids, where a version of the radiation has reportedly been detected in the statistics of ripples. And these are beautiful consistency checks. But they borrow the mathematics without staking the verdict. So the resolution, if it comes in our lifetimes, will likely come the way the islands came, from inside the theory, from someone treating consistency itself as the experiment, the same way a 26-year-old patent clerk once resolved a paradox about light using no instrument but the demand that two good theories stop contradicting each other. It has happened before. The tools are published. The question is stated cleanly at last. Somewhere, possibly tonight, somebody young is reading about islands and feeling the particular itch that starts these things. And the position is open. That is worth saying gently, in the dark, at the end. The island calculations are a first draft, a proof that gravity can balance the ledger, without the mechanism written out. The wormholes sit in the mathematics, waiting to be understood. No experiment can yet reach a real horizon's faint light, and so the resolution, when it comes, will have to be won the way the paradox itself was won, by someone very patient, sitting very still with the equations, refusing to let two beautiful theories agree to differ. Perhaps they are working tonight. Perhaps they have not been born. The universe, in no hurry, keeps its black holes burning at 60 billionths of a degree, holding the question open, 10 to the 67th years of margin, against a species that went from the first flight to the first image of a black hole inside a single century. And there is a last, quiet reason the question refuses to stay academic, which you may already have felt somewhere beneath the physics. Every argument we have followed tonight about a star's information is an argument about yours. The distinctions that make you exactly you, the configuration no universe has repeated, are entries in the same ledger, subject to the same laws, protected, if the verdict holds, by the same impossible-to-burn bookkeeping. The paradox forced physics to decide whether reality's memory is negotiable, and after 50 years of trying every door, the answer that keeps returning is no. Not for stars, not for letters, not for the smallest bit that ever fell through the darkest horizon, and so, by the same arithmetic, not for any moment you have lived. Physics set out to audit a black hole and ended up certifying the permanence of the past. It is hard to think of another technical dispute in any science whose resolution says something that personal. Here at the end, the pieces we gathered through the night can be set down in their final arrangement. The universe keeps a perfect ledger. That was our beginning, the burning letter whose words survive in the light. We then met the one object that seemed built to burn the ledger itself, and followed 50 years of the finest minds of 2 generations. The student with the teacup, the man in the wheelchair calculating in the dark, the accountant in Alberta with his tent-shaped curve, the war, the bet, the baseball encyclopedia held overhead, the wall of fire, the islands, all of it one long audit. And the audit's finding is this: the ledger survives. Every attempt to burn it has failed, at the price of teaching us, page by page, that the ledger is more real than the vault. The pages, it turns out, are not made of space and time. Space and time are made of the pages. And Hawking's beautiful, defeated sentence deserves its final return, because we can now hear what it was really saying. God does not throw the dice where they cannot be seen. The dice were on the table the entire time, scattered through ages of faint light, hidden in plain sight, in correlations we had not yet learned to read. We were not watching a universe that forgets. We were a universe that had not yet learned to read its own memory. So let the black holes keep their long vigil tonight. The one at the center of our galaxy, 4 million suns of patience, and all the others, each one an unfinished question burning at the coldest temperatures in nature. Nothing you did today was lost. Nothing you have ever done will be. Scrambled, encrypted, carried off in light, filed, always filed, never burned. The universe keeps a perfect ledger, and you are one of its entries, and whatever finally explains that ledger will explain everything else too. Thank you for spending this night with the deepest unsolved problem in physics. It is a privilege to sit with these questions in the dark, and a stranger privilege still that the universe lets us understand as much of them as it does. If explorations like this one are how you like to end your days, a quick like or subscribe would mean a great deal. It genuinely helps me keep making these long journeys. And remember, the next time you watch smoke rise from something burning, you are watching information being filed, not destroyed. The universe forgets nothing, and that includes tonight. Good night, and may you never look at a black hole, or your own past, the same way again.